So let's go over this worksheet here, which is nothing more than a review of precipitation reactions or ionization reactions, non-redox reactions. So what do we have here? We have silver nitrate and we have potassium bromide solutions being added together. And we're talking about silver bromide, at least in this paragraph, as a major component of photographic film, which a lot of people don't know what is anymore since we deal in the world of digital cameras. But in any case, we're going to add these guys together. So very simply, we're going to write down the names of these salts, and this will be, let's say, silver nitrate right here. All right, so silver nitrate. Now, the ending name nitrate clues this in on that we're dealing with a polyatomic ion here. And then we have potassium bromide. And the clue there is the IDE ending that tells me it's binary. It's just two different elements. And essentially, this is going to be a double replacement reaction. Some people call it a metathesis, but you should know that the positive silver and the nitrate's a negative ion. The positive ion's always written first in this type of IUPAC naming system, and the potassium is positive and the bromide's negative. The metal are positive ions, they lose. The non-metals gain, become negative. In any case, we're just kind of do-si-do here if you're into square dancing. I am not, but so silver positive will go with the bromide and the potassium goes with the nitrate. So we'll go potassium and we'll go nitrate. So we're just kind of switching the partners as a double replacement works, and we have silver bromide. That's pretty straightforward. Okay, now chemical formulas. Well, silver only really has one oxidation state, Ag+, and nitrate, as we can look up, is NO3-, and there we go, +1, -1. And then we're going to have potassium, which is a +1 ion. Bromide is a -1, so it's a nice 1-to-1. Same thing here, potassium is still +1. You're not going to change the positive nature of it because it's not a redox. And nitrate is NO3, and that cluster is -1, so it's a 1-to-1. And silver bromide is, again, Ag+, Br-. Now, what are the phases? Well, if you know your solubility rules or you have a table that tells you, we know that anything with a nitrate is always soluble, so we write aqueous, all right? That's important. Also, anything with a group 1 ion, okay, any alkali metals are also aqueous because they make low charges, and they're still very big ions, so low coulombic charges between the crystal. And anything with a nitrate or a group 1 ion for 2 rules is also aqueous. You may think because silver is +1 and bromide's -1, these guys have low charges, so therefore they must have low coulombic charges in the crystal that water cannot compete for and break apart. But silver is actually a smaller ion, so it really has a pretty high charge density. So in any case, this is able to attract each other more than water can break apart. So this is a precipitate, and it's one of the halides or halogens, chlorine, bromide, iodide. These guys are normally soluble because they're a -1 charge, small charges, and they're actually big ions to begin with. Both those reasons make them pretty soluble, have low attractions, but they have 3 very important exceptions to the rule: silver, lead, and mercury, and this is one of them. So this is one to think about. So this is your precipitate. Okay, this is the solid that comes out. Now, before we do any type of math, we have to make sure we balance, make sure the law of conservation of mass is working here. 1 silver, 1 silver. When I deal with polyatomic ions, I like to keep them together. So 1 nitrate, 1 nitrate, 1 potassium, 1 potassium, 1 bromide, 1 bromide. We're all balanced. Okay. Now, we wrote this reaction as we would with any kind of introductory type of chem class. But that's not really what's happening here, as I will always mention. Silver nitrate's soluble, so in solution what you really have is free silver ions and free nitrate ions. Same with these guys. So anything aqueous is really not together, okay? So the only thing really comes together is the solid or the precipitate. So what really happened here is the silver ion and the bromide ion came together and they made a solid. Okay, and we can write aqueous here as well. And you can see this is exactly what happened. Okay, so the Ag plus Br makes the solid. The rest of these guys are just what? Spectating. And if we didn't make it precipitate, there would be absolutely no reaction and no net ion reaction to write. Also, we should also think that this is a completion reaction. There really is no equilibrium here. We're really going from left to right until we run out of one of the substances. Okay, so the purpose of this activity, or at least the worksheet, is to find our limiting reagent. Okay, now we can do this through stoichiometry, a long-winded type of dimensional analysis, but I love for you guys to also think in terms of a mole chart, and I think it's helpful for so many of these reactions: speed, accuracy, less chance of an error, and for a lot of problems this is really helpful. But again, if you want to solve for this using dimensional analysis and do a complete Stoich problem, be my host and do that. So I'm going to do here is I'm going to make my little chart here, and this is a mole diagram or a mole chart, and it means initial, change, ending. Okay, so I'm pouring two solutions together, so I definitely know that I have no precipitate initially. How many moles of silver ions and bromide ions do I have? That's where I'm going to have to do some math. Okay, they gave me what? They gave me some information regarding the solution or the moles of the silver nitrate. And what they give me? Well, they gave me the liters and the molarity. And what do we know? We know that molarity is equal to moles over liter. So if I have the liters and I have the molarity, certainly I can solve for the moles. And what's nice about this, again, always thinking about units, okay? Molarity is mole over liter. And of course, if you multiply by liter, you can see that the liters cancel. So that's what we're going to do here. Let's make some room, okay, and just do a little bit of our math here to get what our moles of our initial ions are. So what we have here for silver bromide is we have the 75. So for our silver ions, what we have is 75 liters times 1.25 mole per liter. Liters go bye-bye, and of course, that's going to give us 93.75 moles. Now, careful here. In this example, 1 silver is equal to one of these formulas. And we say formula because it's not a molecule, it's a ratio of ions in a crystal. So because there's 1 silver in one of these formulas, then we know that the moles of the silver is the same as the moles of the silver nitrate. Okay, that's important. If this was Ag2NO3 for whatever reason, if that was the case, all right, we would have to times this by 2. We're always looking at our ratios, so it's just nice. So in any case, let's put that value in as 93.75 moles. Everything that goes in our chart is moles. Let's go now look for the other one. Let's go look for the bromide ions, Br negative. And the information there is we have 90 liters, and we're timesing that by 1.50 mole per liter. And we know the liters go bye-bye, we're left with moles, and we do the math, and we get 135 moles of bromide ions. Again, really it's moles of KBr, okay, but there's 1 Br ion per one of these formulas, so it works out. If it wasn't a nice one-to-one, you'd have to make that adjustment, okay? Any case, so I got 135 that I come down here. All right. Again, moles going in my chart. So there's my initial amount of moles. So I used the molarity to get my moles. Now, looking at my ratio, there's 1 silver to 1 bromide. So that's the stoichiometric ratio. And now we kind of figure out who is the limiting reagent real fast here. If I want bromide to stop the reaction, in order to have all the bromides react, what do I need? Well, I need to have exactly 135 moles. I do not have enough of the Ag plus to make all the bromide disappear. So this is the excess chemical, and this must be limiting. Now, if you don't like what I just said here, we can go the opposite way. If I have 93.75 moles and it's a 1-to-1, I would need exactly what? 93 times it by 1 because it's a 1-to-1. I would need exactly 93.75 moles of silver. Well, guess what? I have more than enough. I have 135, which is more than 93, so definitely I have enough to make silver all react. So what we do here is say that, well, we're going to notice that we're going to use up everything of 0.75. So we're going to use everything of the silver because we have more than enough of the bromide ions. We can't use 135 here because that's all we have. So we're going to use that up, and the change is negative 93.75. And this is also going to be negative 93.75 moles. Why? Well, that's how much of the 135 I need to make all of this disappear. And because it's 1-to-1, it'll be the same. And because this is a 1 here too, this is going to be plus 93.75. Don't forget these mole ratios. One of these and one of these makes one of your products. So when you subtract these go to 0. Okay, and this, of course, 93.75 becomes 93.75 moles at the end. And then here we do the math, 135 initial from our molarity and our liters. We subtract out what gets used up, and now I have 41.25. Remember, everything in here is moles. Okay, so what's the limiting reagent? Again, we didn't have to fill everything out. We could see that clearly from our mole ratio in our chart. I think it's easy to see that the silver ion is the limiting reagent, or you could say what? You could say the silver nitrate. Either one is acceptable. Okay, yes, the silver ion came from the silver nitrate. It doesn't matter. All right. Now the question is, what's the excess reactant final concentration? Well, we know that the excess chemical is the bromide ion, and we know that we used some of it up, but we have some excess. So what we have here is we have 41.25 moles of bromide ion not being used. Now they said final concentration. Okay, don't get lost in the sauce here. We started with bromide ion, potassium bromide, that's where it came from, with what? With a 125, I'm sorry, a 150 molarity and 90 liters. Okay, that's how we've gotten the 135 initial moles. But we poured, these solutions were poured together. Now, assuming that the volumes are additive, okay, and there are scenarios where they're not, but they're telling that they are, how many total liters do I have when I pour these two solutions together? Well, 75 plus 90 is 165 liters. Very simple. So I'm going to take the total moles that remains, okay, and that's this, and I'm going to divide by the total volume at the end of this reaction, which we just realized is 165 liters. This is kind of like doing MV equals MV, okay, where we're solving for the new concentration when we dilute the solution. We're just doing it this way. In any case, you're going to do that math, 41.25 over the total volume, and you get your 0.25 molarity. So their final concentration is 0.25 molar. Now, we're going to watch our sig figs here because we could be off by more than one. Notice I have 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs, ending zeros count when a decimal point is present. So I guess really I should have a third sig fig there. So I have 2, but I wouldn't be able to take off here on plus or minus 1 sig fig is how I normally grade this. But just to be careful, we will put the final sig figs. And this is significant, all right? All leading zeros are not, but ending zeros are if a decimal point is present. So to be very accurate here, that should be the answer. Okay, last little piece, or last couple of pieces. How many grams of precipitate will be produced in this reaction? Okay, well, theoretically, I'm telling you that there was that much actually obtained, but they want to know based on this perfect mass, so I guess I'd say theoretical precipitate, okay, because if you want to do a percent error, okay, this is, they're telling you about 17 kilograms was basically collected, but we're going to calculate how much should be made. Okay, I should really change that. So any case, really easy, because what do I have here? I have exactly how many moles of AgBr would be made from the combination of these two solutions. So I'll start with 93.75 moles, and always write down moles of what, because it gets confusing. In stoichiometry, we start with moles of one thing and we go to moles of another constantly. So this would be AgBr, your precipitate, based on your solubility rules and the information above, and we want to know how many grams. So I'm going to get rid of mole, and converting from molegram is pretty simple. We have to do a formula mass, and then of course 1 silver. That's 1 times 108, which is the atomic mass, okay, which is 108. You can put that in your later of calc if you had to. 1 bromide, and that's 1 times 80, and I'm rounding the atomic masses, and you can do that. We don't need that much precision for these types of problems. So you get 188. At least that's what I'm going to use. That's grams per mole. And I put that on top. And there's my gram per mole there. Okay, moles cancel, so I make sure that I have this set up. And then we do the math. And I get a number, a big number, as expected, because that's a big number of moles. I get a number that's 17625 grams. Now, it'll probably be easier to convert this to kilograms. However, all right, to report 3 sig figs, I probably should show 3, right? Or at least 4 sig figs, because I'm starting with 4 here. Either way, I could do this by going 18,000, or really the best way to show this, big boy, big girl, would be 1 point, if I have 2 sig figs, I would do 1.8. From using 3, let's go with 3. So 1.76 times 10 to the what? 1, 2, 3, 4. And that'd be grams. Okay, and that would really represent our theoretical amount of grams that we would produce in this reaction, okay, based on our starting materials with no error. All right, and you can compare that value to what you actually get to get a percent or theoretical yield. All right, any case, so that's with 3 sig figs. So moving forward, let's do the illustration. All right, now the illustration is there to really help us understand what combinations and who are the spectators that are not involved. Let's start with our solid here. Okay, I'm always put my solid on the side. Now, what is a solid? What's the precipitate that makes a crystalline structure? Well, that's their AgBr, solid. So we should show a 3-dimensional structure of my AgBr. So I'm going to do my Ag plus, Br negative, and I'm just going to put this in a simple cubic structure. All right, and you can always assume that no matter what the charges are, just to show that you're putting these guys in a regular repeating arrangement. I'm just showing attractive forces or ionic bonds. They think of it both ways, but that's my crystal lattice. Okay, it's a regular repeating crystal. This would be another bromide over here and so forth, and this would go on. Okay, so this, if you notice, I have 2 silvers. Now I'm going to go back to my question. The silver was introduced by the silver nitrate. Since the nitrate doesn't make a precipitate, could you say the number of nitrate ions would equal the number of silver ions locked in the precipitate? And I'll say that again. If I have silver nitrate, we introduce silver ions into the net ion from adding silver nitrate, and it's a 1-to-1 relationship. So, party people, as many silver ions that are in the what? Crystalline solid is as many nitrate ions that should be floating around. So when I look at my drawing, I have 2 silver ions in my crystal, so I'm going to draw, okay, 2 nitrate ions floating around. I'm just trying to show that that ratio is going to be the same. Okay, Let's look at the BRs the same way. How were the BRs introduced, or the bromide ions? Well, they were introduced by KBr, and it's a 1-to-1. For every 1 Br, there's 1 K. The potassium nitrate just makes an aqueous solution of free ions. So we should see that because of the 1-to-1 relation of Br to K, we should have the same number of Ks floating around as Br. Since I have 2 here, okay, I'm going to draw 2 K pluses floating around. And I'm trying to draw these random, as this would be a homogeneous mixture called a solution. Okay, so that's pretty straightforward. 2 Ks and 2 BRs. Now, if we stop here, I may have something wrong here. If you look carefully at the problem, who is the excess chemical? We got to think about this. All right, what is the excess chemical? All right, well, who is the excess? Well, we have excess what? The excess chemical was the Br that came from what? Potassium bromide. So I have extra KBr that wasn't used. So shouldn't I add more potassiums than nitrates? Look, for every 1 silver, there's 1 Br. So we had 2 silvers, we have 2 nitrates. You'd expect 2 BRs, but because I have excess KBr. So therefore, I need to show that in my drawing. So the excess KBr means that I should have excess K plus. So I'm going to just add more K pluses to this mixture that should be higher than the nitrates. Okay, and then I'm going to add what? Well, I have to have some BRs. Okay, so I know that I'm having some excess K pluses that outnumber the nitrates, but I have to show some what? BRs. Now notice my BRs are equal to the nitrates, but let's think about that for a second. We know that I have excess. How much excess? And now you don't have to get this crazy. So I know that there's excess Br, so it should be what? Well, it should be equal to the excess K pluses. If this is a K plus that came with this Br originally, then this one would go here. So if you notice, I have 2 Ks that are not associated with a Br negative initially, that's equal to the nitrates. So this would be an appropriate drawing. Okay, so the idea here is the excess chemical I am showing in my drawing. It was KBr, or better yet, K plus ions and Br ions. Okay, nitrate's a spectator. I put 2 into these because I had the same number of silver plus. Now these 2 bromides came from, let's say, these 2 Ks. But because of the excess, the extra amount of these, I add 2 more K pluses to show that there's extra, but I have to also make sure stoichiometrically I add also 2 BRs, the 2 extra. So if I make these guys the 2 extra K pluses, okay, I have to, by stoichiometric ways, put 2 BRs right there. Okay, and that's really important. Okay, so that's an appropriate drawing. It makes you really think. The excess chemical, okay, has to be shown. Also have to think about my what? Spectators. Who is not involved in the reaction? Well, we know the nitrates are spectators, and we know the K plus is spectators, and we know that there's just not enough what? We ran out of what first? Silver ions. So these wind up spectating, but these are part of the excess. Okay, so if you notice, there should be absolutely no silver here because all of it was taken up. Why? Well, because it was part of the limiting reagent. So that is question 1. Question 2 on the other side of this worksheet is done the same way. It's a little bit more difficult because we don't have nice one-to-one relationships, but it's done exactly the same way. Also, I didn't give you liters, you have to convert to liters, but everything's done the same way, okay? So try that on your own, the backside, and please look at the key.